Hello everyone, my name is Haoxiang Ma. I'm very happy to introduce our solution for OCRTOC 2022 on behalf of BUAA-GR team. Before I introduce our solution, I want to introduce our team members first. Haoxiang Ma, Ranqin, Bo-Wei-Du, Jingze Dai, and Professor Di Huang are from Beihang University, LIP Laboratory. Dr. Bo-Yang Gao is from Geometry Robotics. Our solution can be divided to three parts: task planning, perception, and motion planning. Specifically, perception part will output the 6 dimension of freedom poses and grasp poses for each object. It includes 4 parts: multi-view reconstruction, object detection and 3D matching, object pose estimation, grasp detection and grasp assignment. Then, we do task planning to get the move order of the objects. At last, we do motion planning for the robot arm. About multi-view reconstruction, we get multiple real-sense outputs by moving the camera on hand. Besides, we have a Kinect output. We fuse them by camera poses and get a full point cloud with color of the scene. For object detection, first we need a dataset for training, so we generate a RGBD dataset with cluttered scene in Pivot. There are up to 10 objects on table. For every image, we have ground truth of object mask and bounding box. Then, because we want to detect all objects on the table, even they are not in the training set, traditional RPN is a baseline solution, but sometimes it will ignore some objects, so we use an open-world class-agnostic object proposal network. It replaces the classification head to localization quality head, which helps it to detect more novel objects. Besides, we modify network input from RGB to RGBD and fuse multimodal features to get a better result. Here are some visualizations of our results. To get 3D bounding box of objects, detection result from a single view is not enough sometimes, so we do multi-view object detection to refine the result of the main view. If the distances between point clouds in other view and the main view are less than a certain threshold, we combine the point clouds and the 3D bounding box will be more accurate. The next step is finding the match between objects and detected masks. First, the 3D model is projected to many views. Then, we employ an ImageNet pre-trained ResNet to generate features for mask and projected images, and compute the cosine similarity for them. After doing so, for each mask and object, we get a similarity matrix. We employ Hungarian algorithm to find the best match. We do pose estimation by the cropped sense point cloud and the 3D model. We initialize 600 evenly distributed poses and then use point-to-point and point-to-plane ICP. We choose the result with the highest fitness and the lowest RMSE as the final pose. For grasp pose detection, we adopt 2 learning-based methods. We use a detection-based method modified from faster RCN with RGBD input to generate 2D-oriented bounding box as grasp pose. Besides, we use a point-based method modified from GraspNet to generate grasp pose directly. Although learning-based methods perform well for most objects, they cannot generate reliable grasp for small or flat objects like fork, plate, and so on. To solve this problem, we pre-generate correct grasp poses offline by simulation. First, we drop the objects on table to generate some random poses of the object, and then we sample many grasps. Each sample is simulated in OCRTOC simulator in parallel. For grasps detected by learning-based method, we need to assign them to objects. We first crop points inside the gripper to determine the assignment. If the objects are from more than one object, the grasp is dropped. After doing so, we choose the one which has the highest score. In task planning, our main idea is to prioritize moving objects at the top of current scene and at the bottom of target scene. To realize this, we first construct the relation graph for current and target scene, and after that, we search for the moving order greedily. For motion planning, we do two modifications. First, we do path interpolation for long-distance moving to avoid planning failures or singularities. Second, to avoid the collision between the robot arm and objects on table, we build a planning sense based on the result of post-estimation in move-it. Here are some visualizations of our solution. In most cases, our solution shows large improvements. In case 1, all objects have regular shapes, so it's easy to grasp them. In case 2, thanks to our accurate grasp detection and post-estimation, our method can still achieve a good result. In general, our solution works well when objects are easy to grasp and spread across the table, and tasks can be achieved by moving objects to the target positions directly. However, our solution will fail in more difficult tasks. In case 1, plates are in high occlusion, so the detection and post-estimation results are bad. This leads to a large error after the execution. In case 2, the large red box needs to be laid flat on the table, but our method cannot place object in the specific pose. In a word, our solution fails when the scene is in high occlusion and object poses need to be changed in placement. That's all. Thanks for your listening, and thanks to the organizers and other teams.